One of the ways we humans anchor our understanding is through stories that speak to origins. Knowing where we came from is for many a vital step in grasping who we are. Across cultures, many of our forebears took the question of origins to its logical extreme, seeking not just the origin of their group or nation, but of the entire world, the entire universe. The Aboriginal creation myth imagines the sun mother's rays awakening the earth and all the sleeping spirits. Hindu creation stories invoke an unusual blooming lotus that is split into the heavens, the sky, and the earth. And of course, Genesis declares the answer in the most familiar of all biblical phrases, in the beginning. Now, what's remarkable, truly remarkable, is that starting in the first decades of the 20th century, we've been able to pursue theories of creation scientifically. The pivotal moment came with Einstein's discovery of the general theory of relativity, whose final equations he announced to the world in 1915. And shortly thereafter, through the hands of the Russian scientist Alexander Friedmann and the Belgian priest Georges Lemaitre, those equations were wielded to conclude that the universe should be expanding or contracting. Space could not be static, a result that Einstein himself resisted forcefully until Edwin Hubble's observations of what turned out to be distant galaxies all rushing away from us, establishing that space is indeed stretching. And once we knew that space is expanding, it was a comparatively simple matter to imagine mathematically turning the cosmic film in reverse, winding back further and further in time, bringing everything that's now rushing away, bring it all back together, and concluding that in the beginning, everything was compressed into a fantastically dense nugget that underwent a rapid swelling, the Big Bang. The first step in a scientific account of creation. But the Big Bang theory left many questions unanswered, even putting to the side the most difficult of all questions, why is there something rather than nothing? The theory gave no insight into what drove the outward swelling of space in the first place. That is, what was the bang in the Big Bang? And beyond that were important technical challenges. The math showed that if space was even slightly curved near the beginning, then that curvature would grow enormously over time, conflicting with the near flatness of space that we observe today, the so-called flatness problem. And the math? It also showed that if you follow the trajectories of two locations in the early universe that through expansion would now occupy distant spots in the night sky, those locations would have always been too far apart to ever influence each other, too far apart, that is, even for a beam of light to traverse the separation between them since the Big Bang, thus raising the question of how in the world all distant locations in the night sky now have very nearly the same temperature, the so-called horizon problem. Well, it is these problems that a refined version of the Big Bang theory, so-called inflationary cosmology, was introduced to resolve. And so convincing was inflation's resolution that for more than 30 years it has reigned as the dominant scientific cosmological paradigm. But recently, the theory has come under increasing pressure from various camps of researchers who suggest that it may be time to question the dominant paradigm, with supporters of the theory claiming that it is as convincing as it has ever been. In tonight's program, we are honored to speak with two of inflationary cosmology's pioneers who will make the case for inflation, taking us through its discovery and its achievements, and addressing some of the critiques and alternative theories that have recently come to light. Now, for those of you Looking for the final answer? I can give a spoiler alert right here at the top. The jury is still out. That's the nature of science in the making. But the beauty of science is the willingness to challenge accepted wisdom and to trust that observations and data and mathematics will ultimately lead us to deeper insights about the world. So let's begin with the long-reigning inflationary theory of cosmology and two of its pioneers, Alan Guth and Andrei Linde. Alan Guth is a professor of physics at MIT and world-renowned for his discovery of inflationary cosmology, the dominant cosmological paradigm for over 2 decades. Much of his current research focuses on understanding the consequences of inflation's suggestion that there are an infinite number of universes. One of the 2012 breakthrough prizes in fundamental physics was awarded to Guth for the invention of inflationary cosmology, and he shared the 2014 Kavli Prize in astrophysics for pioneering the theory of cosmic inflation. Welcome, Alan. Andrei Linde is a professor of physics at Stanford University and one of the authors of the inflationary theory and the theory of inflationary multiverse. He invented the theory of chaotic inflation, which is the most general version of inflationary cosmology. Linde also helped to develop the theory of eternal chaotic inflation and the mechanism of vacuum stabilization in string theory, which helped to incorporate inflation into the context of string theory. He's the author of books entitled Inflation and Quantum Cosmology and Particle Physics and Inflationary Cosmology. His honors include the Dirac Medal, the Peter Gruber Prize, and the Fundamental Physics Prize, as well as the Kavli Prize in Physics. Welcome, Andrei. Okay, so we unassailably are in a wonderful situation in our quest to understand the origin and evolution of the universe. If we compare our understanding today with, say, the understanding in the late 1800s, we've made enormous strides with Einstein and Lemaitre and Friedman and Hubble and so forth, but we are nothing if not ambitious as a species, and we have sought to push that understanding yet further forward. And of course, both of you have played a pioneering effect, have had a profound impact on our quest to do so. And I'd like to walk through some of the key steps in the insights into inflationary cosmology that both of you have pioneered. And to do so, I want to focus first on some of the well-known tensions or puzzles or problems that beset the traditional Big Bang theory. And just to get us going, perhaps we can focus on two of those, the so-called horizon problem and the flatness problem. Maybe each of you can describe those problems at first, and then we'll turn to potential solutions later on. So Alan, do you want to kick us off? Take your choice, flatness or horizon, it's up to you.
Okay, well, you said flatness first, so I guess I'll choose flatness. Flatness refers to the geometry of the universe. Flat means Euclidean. It doesn't mean two-dimensional, of course. And the point is that general relativity allows the possibility of curved three-dimensional spaces. The universe, according to general relativity, has the possibility of being closed, like the surface of a sphere, or open, which means curved in the opposite direction, which is harder to visualize. Something like saddle-shaped is often used as an analogy. What we know is that the universe today, in fact, looks incredibly flat, incredibly close to Euclidean geometry, and that becomes more and more emphatic as we project backwards in time using the equations of motion that we think describe the universe. So this issue becomes most acute at very early times, and in particular, if we calculate back to what the universe looked like at 1 second after the instant of creation, at that time, the universe needed to have exactly the right mass density, which controls the geometry, needed to have exactly the right mass density to about 17 decimal places to be consistent with what we observe today. And that's an extraordinary amount of fine-tuning. There is nothing in conventional cosmology, by which I mean cosmology without inflation, there's nothing in conventional cosmology which explains why the universe started out so extraordinarily close to this so-called critical mass density. But we know that it did, and that's a mystery. Why did the universe start out so incredibly close to being flat?
So it's not that there's a direct conflict, say, between a prediction of the Big Bang theory and observations. It's more, there's kind of a tension because there's a quality of the Big Bang theory, as you described, that has to be so finely set that we physicists are left scratching our heads wondering how that came to be. All right, Andrei, other problem, the horizon problem. Just give us a sense of what that is.
Sense of disaster. So you had a Big Bang and something banged, and the idea of the old theory was like that. Look at the universe right now. Well, let's go to the past. In the past, it was small because now we know that it grows. So in the past, it was smaller, smaller, smaller. Take all the universe that we see right now. The idea of the original theory was that all particles which exist right now, almost all of them were created from the very beginning. The whole universe consisted of practically the same number of particles that we have right now, maybe like one order of magnitude smaller, but we have about 10 to the 90, 10 to the degree 9, oh my God, big number, particles right now. So we compress them all. And then when their density becomes greater than something which is called Planckian density, we cannot describe the universe with our normal tools. If we would, then we would say it emerged from a singularity. If we would come as close as we can and still say something semi-sensible, but weird, then it is Planckian density. At the Planckian density, the whole universe was of a size, well, a fraction of a centimeter, which is small, but it is just, we package it, all of these 10 to the 90 particles. And this occurred, according to the Big Bang theory, this happened at the moment from the would-be singularity, at the moment 10 to the minus 43 seconds. That's a very, very short time. During this time, light travels at a distance which is called Planckian length, 10 to the minus 33 centimeters. Volume is 10 to the minus 90 of the whole size. So each of these pieces of space contain only one elementary particle. One elementary particle is everything that I can control. Everything else is out of my control. I cannot say, let's create a universe which is homogeneous. Let me say, Alan, you start in the expansion of the universe here nearby. I see you. Let's start. No, Alan would be living very, very far away. I do not even know whether the whole expansion already started. Somebody should give a command, okay, guys, let's start expanding. If nobody gave a command, how is that the universe started expanding at the same time? So that's a problem.
So from a concrete standpoint, many people often point toward the fact that today, if we look out into the universe and measure, say, the temperature of space in widely different locations on the night sky, those temperatures are really close together. We'll talk about a little bit later, they're not exactly the same, but they're very close to the same value. So one of the implications of what you're saying is, that's a puzzle. How could these two widely separated points in the night sky that could not have communicated since the Big Bang, how did they ever get similar temperatures? But again, as with the flatness problem that Alan described, it's not a direct, say, conflict between the theory and observation. It's more a tension. You could imagine, for instance, that somebody set the conditions early on to just be the same from the standpoint of this horizon problem, or someone set the geometry to within that tremendous order of magnitude that Alan described. It's just deeply unsatisfying for that approach.
As I just mentioned, unless this somebody was God who was a causal control of everything, anybody who would try to make a causal impact by sending a message, whatever, he would be unable, just theoretically unable to do this unless there was something specific before Big Bang, and that is like something was before I was born, and maybe I'm lucky to be a professor of Stanford because in my previous life I was a very good dog. Well, I don't know, but we need to have a theory of that, and that's the problem.
Right. So when did people begin to take the flatness problem and the horizon problem seriously?
Alan?
Yeah, I don't know. It was never taken terribly seriously until we had a solution for it, which I think is maybe typical of problems in science. But it was taken seriously by some people, I should say. And in particular, the flatness problem I learned about from Bob Dickey from Princeton University, who was very seriously concerned about it in 1978, I guess. He wrote an article about it with Jim Peebles. So that problem was certainly clearly identified by at least some prominent cosmologists. And the horizon problem as well was talked about in some places in the literature well before inflation came along.
In the 1970s, Alan, you began to think about these issues, and as the famous story goes, in 1979 you had a breakthrough. And can you just briefly describe to us what it is that you found?
Okay. First of all, I was not actually working on either the horizon or the flatness problem. I was not even aware of the horizon problem at the time, but was aware of the flatness problem, but not working on it. I was working on the question of the production of magnetic monopoles in the very early universe. I was working with Henry Tye. We were both postdocs together at Cornell, but this time I had already moved on to a visiting position at SLAC, the Stanford Linear Accelerator Center. And we had discovered together, Henry and me, that naively one would produce a tremendous excess of these magnetic monopoles if one combined what was known about standard cosmology with what was known about grand unified theories. And that was the problem we were working on. We were working on methods of suppressing that. Because
we've never seen even a single one of these magnetic monopoles.
That's right. We've never seen even a single one, exactly. So we were working on mechanisms that would suppress this enormous production mechanism. And we came across the idea that if, as the universe cooled in the context of all of these grand unified theories, the grand unified theories would predict that there would be a phase transition, which we still think is very plausible. And it was at this phase transition that a huge number of monopoles would be produced. We realized that if, instead of the phase transition happening as scheduled, the universe instead supercooled to temperatures far below the natural temperature for that phase transition, then the magnetic monopole production would be enormously suppressed. And what happened one night in December of 1979 is I went back to my rented apartment and carried out a calculation, which I think it was Henry who suggested I do, which is to calculate the effect that the supercooling would have on the expansion rate of the universe. Until this point, we had just naively assumed that the universe would go on expanding exactly as it would have otherwise. But as soon as one writes down the equations, it's actually very obvious that the extreme supercooling drives the universe into a phase of exponential expansion vastly faster than it would have been otherwise. And I came across this fact and did realize immediately that it would solve the flatness problem, which I had learned about approximately a year before. Still didn't know anything about the horizon problem. And I became extremely excited about that.
And so you wrote a paper on this, and was it immediately received as something which was an important new insight? Did it take convincing the community of this idea's worthiness?
Well, it certainly took some convincing. I did not, by the way, immediately write the paper because I still wasn't really clear about how inflation would end. So I held up writing the paper, but did go around the country giving talks about it. From my view, the publicity was enormous. Received an enormous boost from Sidney Coleman, who was a theoretical physicist from Harvard who in fact was visiting at Stanford the same year that I was there. So we interacted with each other. And he immediately became very excited about this idea of inflation and started telling all of his friends about it, which led to a lot of invitations. So within a few months, I was getting job offers based on this new idea, although it took longer before the community as a whole began to accept it.
And Andrei, did word of this result trickle through? Where were you at the time that Alan was doing this work?
I was in Moscow. We actually, in a couple of years before that, were working on a similar problem on this, supercooling in the universe, and then we even found exponential expansion. But then we have found that the universe after that becomes extremely inhomogeneous. So we did not publish anything because it just did not work. And then once it was already, I think, in 80, I was at some seminar which was organized by a Russian physicist, Rubakov. He is a very well-known physicist. And they were trying to solve flatness problem. And I asked them, what is this flatness problem? And they were trying to solve it due to supercooling in Coleman-Weinberg model. And they could not do it. They didn't know how to do it. And the seminar was, okay, so it's impossible to do it. And then I went home a couple of months later. There was a phone call to me by Lev Okunin, another well-known scientist. And he told me, Andrei, did you hear about the preprint by Alan Guth, who is trying to solve the homogeneity and horizon problem using this exponential expansion, supercooling? And I told him, no, I do not know this problem, but let me explain you how it works and let me explain you why it doesn't. So for half an hour, without seeing the paper, I was explaining him all this story, except for it didn't work. So I was really, really upset that I have no idea how to solve it because the idea was so beautiful. And now that we knew, and Alan, you see, that's one good thing about it, which I really like. Alan did not hide the problem. In the end of the paper, I have written that here is what we have. Here is a problem, but let's try to do something. So I was trying to do, and I was so disappointed that I do not know how, that I got an ulcer, seriously.
Seriously?
Okay. I think that this was a reason, because otherwise I was eating healthy and everything, but it was just like I was in a state of depression. And then at some moment, it was in the early summer 81, I realized that, look, if you have this process starting, but not finishing just at once, you have this inflation and then suddenly you don't. Instead of that, you have inflation and then it slowly continues being inflation, just slightly different. And then you end up in non-inflationary stage after a while. Then in this case, this problem of uniformity is solved. So I was extremely excited. I went to call to Rubakov, telling him, because, you know, I wonder whether I'm stupid. This is crazy, but this is really, really simple if you understand it. Okay. And then I called him and asked him, did you hear anything about that? Because this is a possible solution. He told me no. And then I wake up my wife and told her, Renata, I know how the universe was born. So that was, yeah.
I always wonder, I've heard you mention that before. What did Renata say? Did she like, why are you waking me up? So who cares how the universe began? Or was she as excited as you were?
I do not know the details of the discussion because, you know, nevertheless, you do not quite trust it in the first moment after you realized it. So I was trying to telling her that this is how I think it is. But you know what? It is so crazy. So sorry that I waked you up. But maybe, so then for a few months, I'm getting a permission for publication because in Russia, it takes like 3 months to get a permission. This was some months. Yeah. And then Steve Hawking came.
But before we go there, Andrei, I just want to take one step back. So, yes. Alan, so your paper at the end of it certainly did indicate, as Andrei mentioned, that there were certain puzzles that remained with the proposal. But can you just give us a sense of How does this rapid expansion, this inflationary exponential expansion, how does it address the flatness problem? Can you give us just a feel for that?
Yeah, sure. I guess there are different ways of describing it. Probably the most straightforward is the geometric way of describing it. Flatness really does mean geometric flatness, Euclidean-like behavior. And the way inflation solves that really is just that if you take any shape, and it's easiest to picture a sphere, and you just make it bigger and bigger and bigger and bigger, and then look at a fixed amount of space, it looks flatter and flatter and flatter, just like the surface of the Earth looks completely flat to us, even though the Earth is round. So inflation drives the universe to become flat, really, by that very simple mechanism.
Right. And how about the horizon problem? And I'd preface it by saying, every time I've taught these ideas to students, I always get the following question, which I do know how to answer, but I'd like to hear you guys answer it, which is, look, the students naturally say, look, if part of the problem with the horizon problem is that points are too far apart for them to have communicated, would an exponential expansion drive them yet further apart, making it yet more difficult for them to have communicated? Of course, that's not the case, but you can just give us a sense how this rapid expansion can address the horizon problem.
Okay, well, the way I always describe it is I say we can imagine the present universe and model it by the distance between my hands, and imagine following it backwards through time as the universe gets smaller and smaller as we go backwards through time. But then we come to the era of inflation, if we're assuming an inflationary model, and suddenly it starts to get smaller and smaller dramatically quickly. And what that means is that at the beginning of inflation, the region that's destined to become the presently observed universe was vastly smaller than we would have thought in any other theory. And it's while the universe was so incredibly small, as inflation was just beginning, that the homogeneity can be established. And then inflation takes over and just stretches this region uniformly to become everything that we see today.
Great. All right, so this basic paradigm, this basic idea of incredibly rapid expansion is, on the face of it, a potential solution to the flatness problem and to the horizon problem. So, Alan, you described how you got to this idea, thinking about magnetic monopoles, and then Andrei, you briefly described how you took that further. I'd like to just dig into that a little bit more fully. So, Alan, can you describe to us the realization, the initial, say, realization of this idea? How do you get the universe to undergo this kind of rapid exponential expansion?
Okay. I think probably the key point that's most relevant here is the nature of gravity, especially gravity in general relativity. In Newtonian physics, which is the kind of gravity that most folk are familiar with, gravity is always attractive. If you have two masses, they always attract each other. But it turns out that in general relativity, which is, I think, our best modern theory of gravity, gravity can act either attractively or repulsively. There are only some peculiar materials that create repulsive gravity, but it is a possibility. What it actually requires is a negative pressure. Negative pressure is a somewhat exotic concept, but it isn't really. It's just that people don't typically use the word. If you take a piece of rubber and stretch it in all directions, it will pull back. That is a negative pressure. And it does create a tiny amount of repulsive gravity, not nearly enough to oppose the attractive gravity of the mass of the rubber, but that effect is real. And it turns out that there are some materials where this repulsive gravity completely dominates, materials that we know about theoretically or think we can construct theoretically. And inflation proposes, and in fact this supercooled state leads to, exactly that kind of material. A material with a large negative pressure, a huge negative pressure, and resulting in repulsive gravity. And then this repulsive gravity takes over, and the region filled with this matter undergoes exponential expansion.
And so the specific realization of that idea, and I applaud you for keeping the discussion as accessible as possible, but feel free to go even a little bit further here. You introduced what's known as a scalar field with a particular energy curve. We call it a potential energy curve. Want to describe that, because that will naturally set us up for Andrei's next step in this particular development.
Okay, the scalar field describes this phase transition that I alluded to a few minutes ago. The assumption that we were making was that the potential energy function had a little minimum in the center and then went up and then went down and had a much deeper minimum further out. And the inflation takes place when the scalar field is stuck in that little dimple at the center. Classically, it would just stay there forever because there would not be any energy available to take it over the little bump that it needs to go over to start to roll down the hill. Quantum mechanically, it can tunnel through that little bump and then start to roll down the hill. This would not be expected to happen globally. It would be expected to happen locally, where it would start in almost a point, and then that disturbance would grow in the form of what we call a bubble. And the assumption that I started with, but later discovered did not work when I was building this model, but I was hoping that these bubbles would all collide with each other and merge to form a smooth universe. And I spent some time worrying about whether or not that would really happen. Eventually decided, with the help of some other people, that it would not happen. And it was then that I published. And the idea that I tried to convey in the publication was that inflation had the potential for solving these very important cosmological problems, but we don't yet have the right ending. We have to find a new ending if this model is going to work. And that's where Andrei made his first very important contribution.
So we should picture then that there is this so-called scalar field, and it permeates a region of space. Its value is trapped in that particular part of this energy curve, this potential energy curve, and in some region it undergoes this quantum tunneling to a lower value, and that process spreads outward, a kind of domino-like effect in some expanding bubble that allows the field to relax to its lower energy state, and in the process give rise to a realm perhaps that would be like ours, but there are details that challenge that picture, and that's where Andrei comes in. So Andrei, tell us about the next step in this story.
Okay, the next step was what I called new inflation, referring to Alan's paper on inflation. So new inflation was that when the tunneling from the original meta-stable kind of state in the minimum of potential energy, when the tunneling happens, sometimes when this minimum is very shallow, or maybe even almost no minimum at all on the top of the potential, your bubble formed in this process is kind of very shallow, does not differ, the scalar field inside does not differ much from zero, which was originally its value. And therefore, the structure of the vacuum, as Alan explained, the negative pressure there, for a while persisted inside this newly formed bubble, and therefore interior of the bubble also continue inflating. So the bubble inside, in the previous scenario, inside it was already a kind of normal hot universe. But in this scenario inside, it was still inflating universe. And then after a while, the scalar field becomes smaller, oscillates, produces all particles. So that was this new inflation story. So you just have a very similar potential, the same idea of hot Big Bang originally.
So Alan, when you got word got to you about this way of realizing inflation, where the potential energy curve has this change in shape, was this a kind of moment where you like slapped yourself in the head and say, why didn't I think of that? Or what was your response to this?
Yeah, it was pretty much exactly that. I do remember exactly when I first opened the envelope and read the abstract of this preprint. And it explained how the universe could be made out of a single bubble, and you didn't have to have collisions of bubbles, which is what I was trying to get to work but failed to get to work. My first thought was this must be wrong. This we looked at that. Eric Weinberg and I had written a paper about this. So my first inclination was really just after reading the first sentence of the abstract was this must be wrong. But then I read the rest of the abstract, and that's really all it took for me to realize that Andrei was looking at a particular case which Eric and I had failed to look at. And it did sound to me very plausible that that would indeed behave exactly as Andrei claimed in the abstract. And I immediately became very excited about it. I remember I ran through the hallway and walked into the first open office I found. It was Jeffrey Goldstone. And I told him how excited I was about this new paper. And he sort of looked at me like I was crazy, probably. But in any case, I was very excited about it as soon as I read the abstract.
And so, Andrei, you mentioned how the universe can transform from energy within this field, and I don't even know if we've named this field. It's usually called the inflaton field for inflationary cosmology. So there's energy in this scalar field, and you mentioned how as it rolls down, that process can yield the particles that make up the familiar world around us. Can you just tell us about that process a little bit? How does that transition happen?
Well, there are many different ways somebody can give you money. You can rob them, yes. So there are many different ways scalar field can give away its energy. When it oscillates, it is the state where, because of the oscillations, new particles can be produced. People know it in the laboratory. If you have a rapidly oscillating electromagnetic field, for example, if the frequency is large enough, then very, very large, then it can potentially produce electrons. When photons collide, they can produce electrons. So the scalar field, you may imagine that it consists of many scalar particles oscillating in phase, and sometimes they decay into some other particles. And then we also learned, but this was a long time ago, that sometimes they come with a resonance with some particles which stay in the vacuum. And these guys in the vacuum, they get very, very happy. And somebody fluctuates with my own frequency. Or let me do it too. So there is many ways scalar field can give energy. We call this process reheating, because we thought that originally the universe was hot, and now it becomes hot again. The word reheating persists, but the original hot stage is not so necessary.
So the picture then is, at the moment, if we have an appropriately shaped potential energy curve, and if we posit the existence of this scalar field called the inflaton, and if we posit that this field is at a particular place on that energy curve, then coupling that picture with Einstein's general theory of relativity allows for the rapid expansion of space that can resolve the horizon and flatness problem, and can also transform that energy into the particles that make up the world around us. Yes. You took this idea even further, Andrei, to try to make the conditions necessary for this picture to work be even yet more generic, right, in chaotic inflation. You just take us down that.
Well, I would probably be happy sitting with my new inflation story, but some guys, including, Alan Guth, Steve Hawking, etc., they have shown that in this particular, Alexei Starobinsky too, that in this particular model, density perturbations are produced. So the universe originally stretched, becoming homogeneous, it became inhomogeneous later and too inhomogeneous. So then it was necessary to resolve this problem somehow. And it was possible to resolve this problem by reducing coupling constants, coupling of this field to everything else. But if coupling constants are small, how this field come to a state of thermal equilibrium? So I start thinking, do I need thermal equilibrium or not? And let me try to study a theory which has a potential which just like that. Very, very simple, parabolic potential. Some more complicated, but without even any this metastable false vacuum, without high temperature. And what I was found, and it was extremely surprising for me, really, this was one of these aha moments also. Some strange thing happened. I mean, with Alan, we're extremely lucky with these strange moments when you don't know where this goes. So if you start sufficiently high in potential energy, then inflation happens already while you are falling, and it was similar to new inflation. But new inflation, you start with a flat maximum. So it was okay to think that the field rolls down slowly. But what happens if you are on the wall, you're sliding from the wall. The wall is magic in general theory of relativity. Expansion of the universe works like friction for the falling ball. So it kind of sticks, this falling scale field sticks to the wall and slides slowly. And if it slides slowly for a long time, it is almost like old vacuum. And then you have all of this negative tension and you have inflation. And when you write equations, looking at them, solving equations take like 5 minutes. And then you wonder why nobody looked at this. This is so simple.
Right. And in the years since, so we've spoken about old inflation, new inflation, chaotic inflation, different shapes of the curves.
Yeah.
In the years since, how many realizations of inflation have been written down in the literature?
How many types of cheese in Safeway? But we have much more.
Right, right. So this is a general, and I think it's important for people to realize this. Inflation is really a paradigm, right? It's a general set of ideas which envisions that the universe underwent this rapid expansion, but it can be realized in a vast array of different specific models, and we've described some of the earliest ones. Many others have been developed since. So we have this potential theory for explaining the puzzles that we began with, the horizon problem, the flatness problem. What is in your mind, the strongest observational case that can be made for this approach to cosmology?
Alan, do you want to start?
Yeah, I could start. I think I guess I would say there are two incredibly strong pieces of evidence. One is this question of the mass density. Inflation solves the flatness problem in that it explains why the universe started out extraordinarily close to being flat. But it also therefore makes a prediction. Inflation predicts that the universe should start out so close to flat that it should still look flat today. And that's a prediction. And when inflation was first proposed, the estimate was that the mass density was only about a third or a quarter or a fifth of the critical density. But inflation predicted it should be just at the critical density. And now we know that that's true to an accuracy of better than 0.5%. So it's, I think, a very strong success for inflation. And the other class of predictions is really a whole set of predictions about the properties of the non-uniformities in the cosmic microwave background, the ripples on top of this almost uniform distribution of radiation. And inflation predicts a number of features of that, and maybe I'll just mention one and leave some more to Andrei. Perhaps the most salient feature that inflation predicts is that the spectrum of the fluctuations should be very nearly scale invariant. And by spectrum, I mean how the intensity of the ripples depends on the wavelength of the ripples that you're looking at. So inflation predicts it should be essentially the same intensity for all wavelengths of ripples. And that has now been confirmed to a very high degree of accuracy. And I'll stop there in case Andrei wants to say other things.
Yeah, Andrei, you want to push this conversation even further forward?
So these perturbations produced by quantum, quantum perturbations, they sound weird because many people still think that nothing classical can be created from quantum. And then there was many different works on that. One of the people who was in the pioneering in this area was Mukhanov, Alan Guth, Steve Hawking. They all start telling Starobinsky that you can produce galaxies from quantum fluctuations, but it is still too crazy to believe. And now this is a leading theory explaining the origin of cosmic microwave background radiation. For that, you needed to have specific type of fluctuations. They're called adiabatic or scalar perturbations. These perturbations, which are responsible for CMB, are of precisely this type. And yet another prediction, they were supposed to be, and that is mathematical, okay? They were supposed to be Gaussian. And Gaussian is like if you play in casino or you just play with coins, you typically have 50-50 chance that coin lands like that. But if the coin is bent, then predicting something becomes very, very difficult. So the point is that in all simplest models of inflation, the universe does not play with you using bent coins. And then suddenly there were persistent rumors in the beginning of 2010, 2012, there were some rumors that our universe indeed plays with these bent coins, that there are non-Gaussianity of these fluctuations. And if it were confirmed, then 99% of all inflationary models which existed at that time would be completely ruled out. That was a very, very strong result. And then there was a paper, first data released by Planck, and they say no non-Gaussianity to the accuracy with which they measured, and this is colossal accuracy. The universe is consistent with perfect Gaussianity. So they ended one of the big papers, the paper of non-Gaussianity, saying that with this test, inflationary theory passed its strangest test ever. So there were lots of things like that, minor, and then the number of them accumulated. I can count them still on the fingers of all my hands, these evidences in favor of inflation. But so, I would not expect that there will be many when we started doing it.
So it sounds like an amazing set of developments over the course of 30 years. A new way of thinking about cosmological expansion, resolves old problems, gives rise to testable predictions that are confirmed through observations of the microwave background radiation, confirmed through measurements of the flatness of space or the density parameter of the universe being so close to 1 when it initially seemed that it wasn't. All sounds great, but one thing catches my ear, Andrei. You described it as this was a confirmation of the simplest inflationary models. And the reason I pick up on that, of course, is some would say if the cosmic microwave background radiation had a different statistical pattern on the night sky, and we're all familiar with the fact that the pattern that we see, the angular power spectrum, agrees spectacularly with the calculations of the simplest inflationary models. Had the power spectrum been different, a different curve, some would say, well, we could have always engineered one of those potential energy curves describing the inflaton potential to make the predictions match. So some would say, is that therefore a means of saying that the theory is not really falsifiable, at least through those kinds of measurements? What's your response to that?
Okay, I think that you also told several things in one set of sentences.
Yep.
One was kind of engineering. Engineering what? You may engineer a different inflationary model. That is fine, okay? Because like when we study the theory of weak and electromagnetic interactions, there are many different versions of this theory, but it does not take anything from the building principle of all of these models. They're based on the same principle: gauge invariance, spontaneous symmetry breaking, Higgs field, whatever. So that's if you have a different inflationary models, unless they are infinitely ugly, then if they solve all the problems which can be solved only by this method, then that's just fine. But you said something else. We can also engineering something in the universe. And there was some actually suggestion that it is possible to put some inhomogeneities in different places of the universe by hand. Or God gave me the universe like that. Can it be in general possible? Well, and it also doesn't seem very likely because there are several different features of these inhomogeneities. One is just inhomogeneities itself. And another, when you look at the light coming from these places, it's also polarized. okay? And when you try to check whether there is any correlation between homogeneities and polarization, and this was done by WMAP a long time ago, so they concluded that just engineering with density perturbations would not explain correlations between fluctuations of temperature and polarization. So many people tried to do it, of course, and so far it's difficult to do something otherwise. Never say impossible, but that's how it is.
So Alan, when you think about the inflationary theory, do you view it as a powerful mathematical encapsulation of observed qualities of the universe, or do you view it as a predictive theory of the universe? And of course, the reason I ask is because if the theory does have enough flexibility to accommodate a range of distinct observations, and as Andrei says, that's fine, just modify the theory so that it can explain what we observe. Should we view it as an encapsulation of observations in a beautiful mathematical structure, or should we view it as this really predictive theory of cosmological evolution?
Well, I think I certainly regard any specific model of inflation as a predictive theory. And I think it's the goal of scientists, the goal of theoretical physicists, to invent predictive theories and then to compare those with observations and find which predictive theories give the right predictions. And so far, that seems to be the simplest inflationary models. Concerning this argument that if the universe had looked different, we could invent a different theory, I think that's always the case. I mean, if one thinks about the standard model of particle physics, if instead of having 3 gauge groups, there were 8, and if instead of having three generations of particles, there were 12, we would just write down a field theory that had those properties. Quantum field theory is certainly no more predictive than the general idea of inflation is. In both cases, there are many possibilities. Success in science, in my view, simply means finding one theory that matches what we observe to a high degree of accuracy. And how many other theories there are that could have fit different data, I don't see as a relevant question in the least.
So, yeah,
add something to. So we already modified a model of electromagnetic and weak interactions many times.
Yes.
Nobody expected that a mass of the top quark should be almost 200 heavier than a proton. It is just ugly. But we knew that if top quark was absent, then the internal structure of the theory would be inconsistent. We did not know that the Higgs field will be so heavy, and yet without Higgs field, this theory would be inconsistent. So we already in this model, in the electroweak theory, we have approximately 19 free parameters which are already measured and several others which are required to incorporate neutrinos there. In inflationary theory, we have models which require a single parameter to describe everything that we see right now, a single parameter. So when we take bending, fine-tuning, you have one parameter, what bending?
So taking the analogy seriously, just curious what your response is. Quantum field theory as a paradigm is analogous to inflation as a paradigm. The standard model of particle physics as a realization of a specific model within quantum field theory is analogous to any given inflationary model within the inflationary paradigm. Now, to rule out quantum field theory as a paradigm, tough but not impossible, right? If we observed a violation of CPT symmetry, certain fundamental symmetries that would be hard to incorporate within quantum field theory, that would be a piece of evidence that the paradigm was wrong. Is there an observation that you can imagine that would have ruled out inflation as a paradigm? Not any specific realization, but the whole idea.
Let's see, first of all, concerning quantum field theory, you should remember that CPT is a theorem of relativistic quantum field theory, but if you allow yourself to violate special relativity by some small amount, you could also violate CPT by some small amount. So I'm not sure I know of any observation that would completely rule out quantum field theory either. When talking about ruling out the paradigm of inflation, it's a little vague a question because it's There's not really a precise definition of what the paradigm of inflation is. But for example, one thing which has been proposed, which if it can ever be accomplished, I think might be real, is there are some possible mechanisms of seeing in the pattern of perturbations in the cosmic microwave background a way of actually eking out the behavior of the expansion rate of the early universe as a function of time. I'm talking about the so-called clock mechanism of Xinjiang Chen and other people. I don't know if that works, but if it did work and you discovered the universe was actually slowing down during the time that the density perturbations were being created, I think that would be regarded as something that would really rule out the paradigm of inflation as we know it.
Maybe there is another possibility. Inflation does not like producing vector perturbations. So it produces normal scalar perturbations, which are perturbations of density. It produces tensor perturbations, which are gravitational waves, even though their amplitude is very small. And it is very difficult to force them to produce so-called vector perturbations. It's possible if you add something to inflation, like cosmic strings together with inflation, they may produce something. But it is already a very complicated engineering to make it of a type which we could have found, but nobody found these perturbations.
So let's just push this one step further, if we might, to eternal inflation. So if either of you can just give a sense of what eternal inflation is, which takes us to this possibility of a multiverse, which then raises another set of questions that I'd love to get your insight into. So Alan or Andrei, eternal inflation, where does it come from? What does it mean?
What happens is that when I told you about scale field just sliding, okay? Or when Alan told you about the scalar field producing bubbles, or when we mentioned the scalar field standing on the top of the hill, and that is then not only my work, but also Vilenkin. If you stay on the top of the hill, you can partially fall down, but somebody will stay standing, stand on the top of the hill, and the universe at that time will expand. In Alan's scenario, you produce bubbles, but the space in between them continue expanding. And what I have found that even if you are on the slope of the hill, like in chaotic inflation scenario, then if you are high enough, if you're high, you can do many different things. Scalar field can also jump upwards higher than it was before against all expectations because of quantum fluctuations. And then it starts producing new and new parts of the universe, and this process goes on eternally. So this is one possibility. And this possibility by itself is kind of not very interesting. It's interesting because it tells you something about the general global structure of the universe. It's more complicated than I expected. But what happens is that these quantum fluctuations induce quantum fluctuations in many other fields present. And they can take scalar field responsible, for example, for electroweak theory and bring it to a different position. And you can then end up in the universe, some parts of which chaotically have one set of properties and some parts have a different set of properties. It's nothing metaphysical about it. It's just physical process which does it. Okay, so then the universe in different parts, it becomes different from each other. And okay, nothing wrong. It's once again, I'm not imagining like different parallel universes and jumping from one to another because you commit a crime in one and you will be saved in another. We're just having different parts of the same universe and they have different properties.
And so from the maximal bird's eye perspective, these different realms where the quantum fluctuations have resulted in different cosmological evolution, different properties, oftentimes people do use the language multiverse, calling each of those realms a universe. It's totally language, as you're saying. It's less mysterious than perhaps it sounds. It's just different realms that, because of these quantum fluctuations, have different properties. So, Alan, in thinking about this fairly generic property of the inflationary paradigm. It's not impossible to avoid the multiverse within inflation, but many of the models that people write down do yield this conclusion. You have famously said, in thinking about all these different realms, something of the sort, and do correct me if I'm wrong, anything that can happen will happen an infinite number of times. So is that a correct paraphrase?
That's a correct quotation, yes. Yeah, I think it's an exact quote.
Great, perfect. So just explain to us what exactly that poetic statement means in this context.
Yes. Well, I guess the language I like to use to describe what Andrei was talking about is, in this eternally inflating background, one has local big bangs, local events that look just like our Big Bang, each of which leads to a kind of a universe that follows it. I call it a pocket universe. We'd be living in one of those pocket universes. And describing it in that language, these pocket universes go on being created forever, and in fact, they're even created at an exponentially expanding rate, according to the simple model. Extrapolating the model to infinity might be a stretch. We don't really know for absolute sure that this is the right thing to do, but it's more or less the only thing we know how to do, so we pursue those consequences. That means that there's going to be an infinite number of universes, and if there's only a finite number of possibilities, which very likely seems to be the case in a quantum system, then every one of those possibilities has to be realized an infinite number of times. And that's what we would expect in the context of this model.
Now, there are some weird consequences of that I don't really want to spend much time on, because I'm tired of talking about it. I think you guys are too. The possibility that there are copies of us out there, all that sort of wonderful stuff that can keep science fiction writers busy for a very long time. But from a scientific standpoint, this does raise an issue that some of our colleagues have emphasized vociferously, which is, if there are these infinity of universes where anything that is allowed by the laws of physics can be realized, then it suggests that any observation that we have made of the universe can be accommodated in one of these universes out there. So rather than inflation being a predictive theory of the world, all observations do is they point at which of these universes we happen to be in, but there would always be a universe which could accommodate the observations, and therefore the theory is unfalsifiable, it's not predictive. What's your take on that?
My take is that it's a pretty misguided point of view. I think one could say similar things about quantum mechanics, which is in fact where all of this uncertainty arises from. Quantum mechanics says that there's a vast array of things that are possible, and that's all we're talking about in inflation as well. It's everything that can happen, meaning everything that's allowed by quantum mechanics. And quantum mechanics itself says that anything that's allowed can actually happen. The point is that there are probabilities involved. Quantum mechanics is a probabilistic theory. It does not allow us to ever, whether we're talking about inflation or chemistry, it does not allow us to ever make precise, reliable predictions. All we can do is predict probabilities. And the same, we hope, is true for the multiverse model. Now, it is true for the multiverse model, there are new problems, new questions that we're not sure how to answer. Because the model is predicting that all possible events are going to occur in infinite number of times, it's harder to know what you mean when you say that some type of event is more common than another type, since they're both going to happen an infinite number of times. So we're still working on that, but I should say that it's not what appears to be a completely insurmountable problem. We certainly can propose and have proposed recipes, procedures for defining probabilities, which give reasonable results. What we don't know at this point is how to decide what's the, in principle, correct way to calculate probabilities in the multiverse. And that really is a fascinating problem.
So Andrei, I'd like to come to you in half a second, but I just want to push this with Alan one step further. So, as any undergraduate student in quantum mechanics knows, the probability that the theory provides has a very precise mathematical articulation, the so-called Born rule, take the norm square of the wave function. We all learn it when we learn our basic quantum mechanics. That rule, that recipe as you describe it, is currently missing in the inflationary paradigm. And the question that arises is, without that rule in quantum mechanics, we wouldn't be able to say anything at all. Quantum mechanics really wouldn't be a theory at that point. It would just be an interesting collection of ideas. Without that rule in the inflationary paradigm, are we not in a similar situation?
I guess I don't think so. Whenever physics expands from some realm to a bigger realm, non-relativistic mechanics to relativistic mechanics, classical mechanics to quantum mechanics, one has always relied on the principle that the new rules, even before they're fully known, have to be consistent with the old rules, where those old rules have been tested and where they apply. And I think the same is true here. Even though we don't ultimately know how to define probabilities of events in the multiverse, I think we still know perfectly well by the old-fashioned principles how to define the probability that a coin will come up heads or that a Stern-Gerlach experiment will turn out a certain way.
Even when we're talking about the infinite number of realms, and therefore we need some sort of means of taming that infinity, you're confident that that rule will naturally emerge from our more basic understanding of probability, even if it hasn't yet reached that stage. Is that an accurate?
Yeah, that's exactly what I'm saying. I'm saying although we don't know the right rules for sure about the multiverse, they have to be consistent with what we know locally.
And Andrei, what's your take on and maybe we should name this, it's so-called measure problem in inflationary cosmology. What's your view on this issue? How important is it? How vital is it? Are you, in other words, you've described how, you got, ulcers over the original problems of cosmology. Does the measure problem, has it given you ulcers, or will it give you ulcers, or is it not as bothersome?
Joke aside, I remember how I started being a physicist. It was in '71. I was still in Moscow State University, and the professor teaching us quantum field theory and axiomatic approach, he told us, guys, do not go to theoretical physics because it's that field. I know it because axiomatic field theory is the only thing which is a good theory. It must explain everything, but it does not, and it's a dead end. The greatest accelerator ever built presently is our accelerator in Dubna, does not produce new results, so you're doomed, okay? But because I was already in theoretical physics and it was my fate, who cares, Dubna. So I went to my thesis advisor, Professor Kirzhnets, in the early January '92. And he told me, and I told him, let's publish my thesis where I was developing different regularization procedures for electroweak theory. And all of these regularization procedures, when gauge dependent, produced meaningless results, and we did not know which measure is more and less meaningless than another. It looked hopeless. So next day when I came to his office, he told me, Andrei, forget everything that you did so far, because we now know that electromagnetic and weak interaction theory is renormalized. This is a preprint describing this paper by Guth. Everything changed overnight. So it is this problem of how to define things when you meet infinities. There are some methods to think about it. And when everybody tells you that this problem is unsolvable and do not, well, even think that you can find a solution, I think that it's silly. So that is one thing. Another thing, just like when we are picking a good model, we are trying to compare it with experimental data, and then we rule out the model. We may come with some probability measure which seem reasonable, And then we fall in love with this probability measure. There was a probability measure I fell in love some time ago. And then it was found that this probability measure predicts that you must be born in the hot soup. And I think that I didn't. Okay, so this means that this probability measure is experimentally ruled out, independent of anything. So we do not know which of the probability measures are better, but we definitely know which ones are already ruled out, just like with elementary particle physics. So there is definite progress, but there is something else which we must work on before we even will come to this. It's like with Schrödinger cat. For 100 years, we're still debating the question of reality of a second copy of a Schrödinger cat. If we see hungry cat, what's about with a dead cat? How to interpret quantum mechanics? Here, we're trying to ask questions like that. Why have you been born in this universe with these particular properties? Or surely it means that we are born in the most probable of all possible universes. We just must establish the measure which tells you how probable it was to live here. But think about our Earth. If not for internet, if not for this travel, etc., if we were born a few thousand years ago, we would not know anything about China, okay? And if we count how many people live in China and think that we must live in the place where all live, so to say, then to be born Russian would seem to use wrong probability measure or something. So it looks like we need to learn how to ask correct questions. And the very fact that we are forced right now to merge to discussion of questions which previously were considered metaphysical, I think it is to the great benefit of all of us.
So let's imagine that one day we do have this probability measure in the inflationary paradigm, and that the measure does what we would hope it would. Namely, it says that the kind of world that we are in, the kind of universe that we are in, is highly likely, highly probable, and all the other realms that eternal inflation says are out there are much less likely, much less probable, and that gives us some explanation for why it is that we are here. The question is, in that scenario, how much success of the theory is due to the inflationary paradigm per se, and how much of the success is due to this measure? Because one could have said way back in the early days of the Big Bang Theory, if we just find the right measure that makes the conditions necessary for flatness to be highly likely as opposed to unlikely, or if we find the right measure that correlates somehow distant locations that seemingly can't communicate, if we just find the right measure, then we will have resolved those problems. So to what extent would the success of inflation plus a measure be due to inflation as opposed to due to the measure?
How about creating any other theory which would predict what inflation already predicted, like all of these miracles of adiabatic perturbations, Gaussian perturbations, flat spectrum, flat universe, etc. How about somebody cook up a theory like that? Then we would have a reason to compare what is due to the idea of inflation or what is due to the chance. So when too many things happen by chance, but you have a theory, however incomplete, which predicts exactly this and continue predicting year after year, then, well, you have a good idea what you should use in your life.
So my question to you, or even to both of you, would be, and I suspect I know the answer, but I'd just like to hear it directly. Had the observations not given rise to omega very close to 1, had the observations not given rise to adiabatic spectrum of perturbations as we observe in the microwave background radiation here, had that not been the data, you would not have said there is another realm in eternal inflation that can accommodate those observations and therefore inflation is fine. That would not have been your response. Is that correct?
Yeah, I think so. I think we are looking for a theory that predicts that what we observe is probable. And we're not finished unless we can do that. We certainly have not completely done that, and that we still, I think, want to be able to solve this measure problem. But I think the criterion that we use is the same as criteria that I think any scientist uses. A theory is good if the predictions of the theory agree with what we see.
And I sometimes answer a similar question in the following form. You know, if I have lots of issues with my predictions, but there are some predictions which come right and which we still do not know how to interpret in terms of any other theory. Like, for example, if we predict Gaussianity and then the model must be complicated to account for non-Gaussianity, I would say you have two choices. Either to start everything from scratch, forget about inflationary theory, just produce any theory. But then I need to have a theory which, first of all, explain why it is so homogeneous, why fluctuations are so small to start with, and many other things which are done by inflation. Then we would have something to compare with. So my way of formulating it was as following. If your roof starts leaking, you do not destroy a house and go to sleep on the bench. You try to patch the roof first. So this is, if the problems are such that we cannot solve them, then it will be a time for us to look for something better. It's always good to look for something better.
Right.
But then it would be pressed to.
So if the inflationary specific model necessary to explain observations were to become so baroque, where you had to patch together, as you say, that roof is now looking extraordinarily ugly, you would say we've probably hit the end of the line. But insofar as we've not gotten to that place, you're still extremely bullish on this approach. Is that correct?
With one parameter, which is sufficient to describe everything that we want to get from inflation, it is definitely not so baroque.
So if we turn now to the future and envision what might happen in the next 5, 10, 15, 20 years, are there any ideas currently on the table or on the horizon, other approaches that are not inflation? Do any of the ideas that people put forward strike you as promising, worthy of attention, a potential competitor to this approach going forward?
Well, I remember a moment when we received the first preprint about ekpyrotic scenario. And it looked like thick, very large preprint. And you open it, and there are magic words about string theory and solving all problems. And here's a mechanism how to solve the problem. And Renata, my wife, she is an expert in supergravity and string theory. She started reading it in parallel. And then it looks like, great, we have another solution. So if it works like that, if, as they say, they produce perturbations also with a flat spectrum, slightly different from inflationary, so it's fantastic. Maybe we need to switch because we have this very interesting solution. So then I continue reading. And half an hour later, I asked Renata, well, please look at it. Where do they come this with? And she said, no, this is in string theory, it's different. Then I continue reading. Then she continues and say, Andrei, where this came from? They say that the universe is homogeneous because it was created by colliding brains, which were completely homogeneous to start with. So how does it solve the homogeneity problem if you must assume homogeneity to start with? Then we continue reading further and further. And then the question arises, are you sure that these two colliding brains really lead to Big Bang? So it happened that no, they actually lead to Big Crunch. How is that? This is a paper. This is so many different statements. They're just wrong. And then they develop a theory of perturbations, which were supposed to replace theory of inflationary perturbations. And then several people for several years studied it, and they came to a conclusion that these perturbations are not generated at all in this scenario. After that, they replaced the scenario, they replaced it by something else, they replaced the theory of perturbations. And this continues like that. So for a while, I was continued to following it. But unfortunately, this pattern, it was kind of self-reproducing. In one paper, they kind of trying to address what is another, suggested something else, which was difficult to address. And each time it looked like here is another great way of solving the same problem. So for several years, I following, then continue following, and continue following. And then people start getting kind of disappointed. And then the same people, they start, maybe because they, did not have a finished product, they started saying, no, well, but inflationary theory is also good. And in fact, it's much worse than ours. So this is like that. So it is possible that something will happen from what they study, in particular, if people solve the singularity problem, which is what they're trying to do. It's great. And for inflation, it really does not matter how you solve a singularity problem, because you can restart creation of inhomogeneities later when inflation starts. So inflation kind of agnostic to what happened, almost agnostic to what happened before the gravitational collapse, etc. So if somebody solves this problem, we will be the first people to be absolutely happy, okay? But if you assume that for completeness of theory, you must produce perturbations before the singularity, and problem of singularity is unsolved, and you must trust that when you go through the singularity, then the same perturbations are preserved. And then this was the original idea, which did not work. It was replaced by something else. So it is kind of complicated. But if the problem, singularity problem, will be solved whatever way, not necessarily their way, we will be ecstatic.
So going forward, thinking, however far into the future seems natural, what do you consider to be the next breakthrough in, say, the inflationary approach? Is it finding an inflationary measure? Is it discovering the B mode imprint in the microwave background radiation, theoretical, observational? Just take it wherever you think it might go. Were we to have this conversation at the World Science Festival, say, 5 decades from now, what will people be talking about? Andrei?
Well, I would say let's try to do first thing first, if possible, because there are some things which do not depend on interpretation and probably not on the probability measure. Like we may find gravitational waves produced during inflation. We may not find gravitational waves, but this is a no lose proposition to look at them except for losing money. Okay, but okay, who cares about money? Now, what is important that if you find evidence for gravitational waves, you remember what happened when the gravitational waves produced by colliding black holes were found. It was a massive enthusiasm. It was incredible discovery. It was for the first time you see degrees of freedom of space-time itself. It is like space and time is alive. That is incredible. But if we find gravitational waves produced by inflation, it is even bigger, because it is testing quantum gravity at energies 10 orders of magnitude higher than energies which can be achieved at any accelerator. So it's incredible. That's one thing. Another thing, when we are choosing between different models and we are trying to see whether models which are required are too exotic or not, if we know something which is called flatness of spectrum, the perturbations are predicted such that on the logarithmic scale, all amplitude of all perturbations must be almost constant, slightly not constant. Okay, so this is something that we know, but this slightly is already a prediction. For each model, we know how slightly non-constant it is. And by finding this experimentally using WMAP satellite, by Planck satellite, by measuring this, we now know this parameter with accuracy close to better than 1%, okay, which is very good. So But by doing that, 99% of inflationary models which existed before these experiments, they're just ruled out because they were showing all, and now we have some particular angle. Now, expectations are that this parameter will be measured in the future 10 to 15 years with accuracy 2 times better. And they is really killing for many models which exist right now. It will be very difficult to squeeze into the, okay. So this is the way to use our universe as an accelerator, where you are not trying to prove or disprove standard model, but you are trying to find out what is the standard model, what are the parameters there. So we know the parameters with accuracy much, much greater than before.
Alan, want to have the final word on where things are going?
Okay. Well, extrapolating beyond what Andrei talked about, which is kind of the next decade, your question was 50 years from now. So certainly, I'm sure none of the three of us could do an accurate job of predicting what we'll be talking about or what other people will be talking about 50 years from now. But certainly on a 50-year time scale, I think we can hope to have a solution to this measure problem and a much more detailed understanding of what a multiverse might actually look like. And one thought that I'll throw in is that so far we've pretty much been thinking about the multiverse in a semi-classical way, where we're really thinking of the space-time being described classically, and there are tunneling events that we think of describing quantum mechanically, but we don't really build in the full quantum mechanics into the description of the space-time itself. That is the business of string theory and other versions of quantum gravity. And I would hope that within 50 years, that program will have made tremendous progress. And that's really where I look to as the most likely place for solving this measure problem. I think it really is a question of knowing how to count regions of space-time. And I think a real quantum theory of space-time will very likely shed light on that question.
Yeah, I mean, how amazing would it be if not only those developments give us the probability measure in inflationary cosmology, but give us insight into solving certain foundational problems in quantum mechanics, such as how to deal with the so-called quantum measurement problem there. Maybe there's insight that each problem can shed on the other. That would be quite a wonderful development. So thank you both for this conversation on the inflationary theory. And obviously, best of luck going forward in solving some of these key unresolved mysteries.
Thanks.
It's great talking to you, Brian.
Thank you.